Okay, so today we're going to combine the objectives of the last two videos and put it all together and come up with some decent sketches for rational functions. We're only going to do one example in the video because these examples can be kind of long. And I think this example will contain all the different elements you're going to encounter when you graph rational functions. So we're going to try to sketch a nice graph of this rational function right here. And before we get going, I just want to point out that there's going to be three different forms that you're going to encounter when you do this correctly and fully. So we have the given form, which is the polynomial divided by polynomial form. So I have polynomial in the numerator, polynomial in the denominator. You're going to want to have at some point the factored form, where the numerator is completely factored and the denominator is completely factored, and that's where your factoring skills come in and your rational root theorem may come in from time to time. And then there's going to be the long division form. Okay, so I've done the long division of numerator divided by denominator, and I've obtained some kind of result in the form q of x plus r of x over d of x. So I'm not going to actually show the steps to putting the function f into these forms. I'm going to assume you have that skill from before, and you can do that. So I'm just going to jump in and say that I've taken f in the standard form, and I've already factored it into its factored form. Okay, so the first thing I'm going to do once that's done is create my sign chart. Some of you have asked, is the sign chart necessary to graph these? And I guess it's not necessary, but I find it helpful. So I'm going to continue to do it. And it helps me down the road when I'm trying to fill in the pieces of the graph. All right, so what goes on my sign chart? Any numbers that make my function 0 or undefined. So I look up here, and the zeros in the numerator would be positive 1, negative 1, positive 2, and negative 2. I look at the denominator, and numbers that make the denominator 0 would be negative 1, which is already here. I need a negative 6, so I'll go ahead and extend this a little bit. I need a positive 2, which I already have. Okay, now I need to do some sign tests in each interval. So let's start with a number like 10, and I look at my function f in factored form. I'm going to plug the 10 in and see what kind of signs I get. So here's a plus, that's 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 a plus. Everything's a plus. So positive in this region right here. All right, now let's plug in 3 halves for this interval right here. So this is a plus, that's a plus, that's a minus, that's a plus, that's a minus, that's a plus, and this is a plus. So I've got all pluses and 2 minuses, so overall we have a plus. I can use 0 for the next interval, which is nice. And really, if I want to go back to the standard form, I can just look at this and use 0, plug it in, and see I'm going to get a negative, or a positive 8 divided by negative 12. So a negative would be shown in this interval right here. All right, negative 1.5 for this interval here. That's going to be a minus, a minus, a minus, a plus, a minus, a plus, and this is a minus, but it's squared, so it's a plus. So let's see here. I've got 3 positives and 4 negatives, so overall that's a positive. We can use negative 3 in this region here. So minus, a minus, a minus, a minus, a minus, a plus, and then a minus squared is a plus. So now I've got 5 negative signs and 2 plus signs, so that's a negative overall. And then I can use any large negative number I want for the last interval. So a minus, a minus, a minus, a minus, a minus, a minus. This is a minus squared, so it's a plus. That gives me 6 negatives, 1 positive, so overall positive. So I have my sign chart for f of x. And I'm going to go ahead and copy and paste this into my page that's going to have the graph, and paste. So I can use this later on. Okay, now that I have my sign chart done, I want to make note of some other features that I see on the graph here. So first of all, where are the zeros of f of x? So when does the numerator equal 0 but the denominator not? So I can look up here. Looks like x equals 1 is good. X equals negative 1 is a problem, so I'm going to hold off on that because that's a 0 over 0 issue to handle. So we'll handle that in a second. X equals 2 is also a 0 over 0 problem. And x equals -2 is just a 0 for the numerator, so that one's good. We then look for vertical asymptotes. That's when the denominator is 0 but the numerator isn't. In other words, when I get a number divided by 0. So I've already seen that -1 is a 0 over 0 issue. -6 makes the denominator 0 only. So there'll be a vertical asymptote at -6. And +2 needs to be investigated. Okay, so we need to investigate these two issues here. What happens when x is -1 or close to -1? And what happens when x gets close to 2? So what we want to do now is take our function f of x and remove any factors that are making this be 0 over 0. Okay, so we're going to say for every value of x except these, okay, for x is not equal to -1 or 2, f of x is the same as a new polynomial or a new rational function. So what can we do? We can remove an x minus 2 and an x minus 2 as an unnecessary one, and we've already noted that x can't be +2. And we can remove an x plus 1 and one of the x plus 1s in the denominator. So that leaves us with 2 times x minus 1 times x plus 2 in the numerator. And that leaves us with x plus 1 and x plus 6 in the denominator. And now we can investigate what happens when x gets close to these numbers, -1 and 2. So, as x approaches -1, f of x will approach, and what I'm going to do now is I'm going to plug in -1 into what's left of this function here. So I'm going to get 2 times -2 times 1, which I think is -4, and the denominator will be 0 times 5, or 0. Okay, this tells me there's going to be a vertical asymptote at x equals -1. So I'm going to add that to the list over here. Let's do the same thing for x approaching 2. So I'm going to plug in 2 into what's left. I know I can't plug in 2 into the original f, but the modified f I can plug in 2. I'm going to get 2 times 1 times 4. So that's 8 over 3 times 8, which is 24, which will simplify to 1/3. And so there is a hole, or a removable discontinuity, at 2, 1/3. So let's add that over here. One other feature I always like to add is the y-intercept, which we've already seen is 0, and you know what? I forgot what it was, so let's go back to the standard form. It's -8/12, which is -2/3. Good. And now let's copy and paste all this information into the graph page. And now the last thing to do is to look at the end behavior. And so for the end behavior, we do the polynomial long division, and we obtain this form. I'll skip the work of the division, just go with it, and if you want to check it, you might. But what we know is that when we do long division, the quotient ends up being the end behavior model for the function, and when that quotient is a constant, in this case 2, we know that y equals 2 is going to be a horizontal asymptote for f. So that's my end behavior. Okay, let's start with the dots that we know. So we have zeros at x equals 1. So we can place a dot there, and a 0 at x equals -2. And we have a y-intercept of -2/3. So that's going to be pretty close to the x-axis. Let's say it's about there. And next we can plug, we know there's a hole at 2, 1/3. So I can go ahead and place that on the graph right there. And now we have some vertical asymptotes, which I'm going to denote with dotted vertical line. Vertical asymptotes occur at -6 and at -1. So -6 and -1. And now we are ready to try to connect the dots and as much information as we have using the sign chart. So let's start at the y-intercept, which is 0, -2/3. And we're going to head towards a vertical asymptote. That vertical asymptote's at -1, and I look at the sign chart, and it says before -1, your function should be negative. That makes sense because I'm already at a negative number, and I can't cross the x-axis because I would have already had a dot plotted to do that. So as I approach this vertical asymptote, we're going to shoot downward, approach negative infinity. All right, and now let's work to the right first. So we're going to go connect the dots to the 0. We're going to go through the removal of discontinuity, skip over 2, 1/3 in this case, and then my end behavior says y equals 2 is a horizontal asymptote. So as I head towards infinity, my graph's going to flatten out until the y values are basically 2, the farther I go to the right. So something like that. All right, on the other side of this asymptote, at x equals -1, my function is supposed to be positive. So I'm going to come up from positive infinity for the positive part, and I need to come on down, and I obviously have to hit this dot at -2. What happens after or before -2? My sign chart says I should be negative. So I'm going to cross through the x-axis there, and I'm going to head towards this vertical asymptote here at -6. My sign chart says you need to be negative before -6 and after -2. So we're going to cross on through. We don't know exactly how this thing bends, but it's going to head towards this asymptote and shoot on down to -infinity. On the other side of the asymptote, we need to be positive. So we're going to come from the top, and we're going to come on down, and my end behavior says approach y equals 2 as a horizontal asymptote. So we're going to flatten out. So that is a sketch of what we should see. Let's go ahead and see how good the sketch is by comparing this with GeoGebra. Okay, so here's the same grid, same coordinate system, and now I'm just going to show the graph that I had already programmed in here. And there it is, and that more or less looks like what we graphed. We see an end behavior, y equals 2. It's a little bit shallower in the beginning than I had, but eventually it's going to get to y equals 2. Same thing on the left side here. We had the correct behavior around the asymptotes. We don't see the hole that is plotted because GeoGebra is not in a window to show a hole, but if we tried to find a value at where the hole is, we wouldn't find one. We see the y-intercept looks like it could very well be -2/3, and we see the zeros that we plotted on our own graph there. And just to compare both pictures, here's our picture, and I go ahead and insert the picture file from GeoGebra just taken. Okay, if we try to superimpose these on top of each other, we can see they're very, very close to being the same. There are details that calculus will help us with next year, but that's a pretty good sketch for just things we can do by hand without calculus.